Let's talk about distributions. Distributions are mathematical functions that describe the likelihood of different outcomes in a given set of events. Look at this graph, for example. It shows the holy grail of distributions, the normal distribution. We see that there is a central value, which is the most likely to happen. And as we progressively move away from it in either direction, the likelihood of the outcome decreases in symmetrical fashion. You'll see this pretty much everywhere in data science. And we'll come back to it later, too. Now, distributions can be of two kinds: discrete and continuous. Discrete distributions are applicable when there's a finite number of outcomes. For example, when determining the probability distribution of a coin flip, we only have two possible outcomes: heads or tails. On the other hand, when we're talking about modeling a person's height, there is no set number of outcomes. This is a continuous function. The three most common discrete distributions are the binomial distribution, the Poisson distribution, and geometric distribution. Each one of these gives an answer to different kinds of questions. We use binomial distributions for experiments with two possible outcomes, which we call success and failure. The binomial allows us to find out how likely it is, when repeating this experiment n times, to have x successful outcomes out of those n trials. Let's say we flipped a coin 10 times, and for each set of 10 flips, we'll then note down how many heads we get. Here on screen, we simulated 10 flips and got 4 heads. If we repeated this thousands of times and plotted the number of heads we got for each repetition, this is what it would look like. Now, the caveat here is that you need a fair coin. If, say, we had a 65% of probability instead of 50-50, this is what the plot would look like. And if we had a 90% of getting heads, this is what it would look like. Luckily, if you know the probability of a successful outcome, you're set. The formula you see now on screen is all you need to calculate the probability of x successes out of n trials. The first factor determines the number of combinations, which we multiply by the probability of success repeating x times, and consequently failure resulting out of the remaining trials. When using the Poisson distribution, we tend to think of the number of events in time intervals rather than number of successful outcomes. Take, for example, the number of car accidents that happen in a city every day. You can't count how many cars exactly are circulating, so we take the mean number of accidents every day. This is the only parameter required for this distribution, and it is called lambda. By knowing this, we can find out how likely it is to have X events in a time frame. In this case, knowing the mean number of accidents, we can work out the probability of X accidents happening on a given day by using this formula. Finally, let's talk about the geometric distribution. This helps us calculate how likely it is that we need X trials before our first successful outcome. The formula to find this out is the simplest. Since all trials result in failures until the last one, we multiply the probability of success by the probability of failure elevated to the x-1 power. You might be lost now, but just bear this in mind. The most important thing right now is to know what questions these distributions give answers to. You'll soon find out how to use this knowledge too. Now, continuous distributions. The most frequent ones are the exponential distribution, uniform distribution, and the almighty normal. The exponential distribution allows us to determine the likelihood of a set distance in time between two Poissonian events. In the car accidents example, this would allow us to model the distance in time between two accidents. The function that describes this distribution takes the same lambda parameter we had in the Poisson distribution. As you can see, the time interval isn't necessarily fixed, but it varies from 0 to possibly infinity. We use uniform distributions when the only thing we know about the data are its upper and lower bounds, without any other information. The probability assigned to each point between the two extremes is exactly the same, and we find it through this formula. All of the points outside of the limits are given a probability of 0. Now, back to the normal. We've already talked about its symmetrical bell curve shape and all that cool stuff, but it has one property that just makes it so powerful, which is called central limit theorem. This states that the sum, or average, of a large number of independent random variables, regardless of their underlying distribution, will tend to follow a normal distribution as the sample size increases. This also explains why the normal distribution is so common in natural phenomena, as these are often the result of long lists of causes.